Exploring and producing oil is an old and mature industry. Many lessons have been learned since these Azeris labored to win the mineral from the ground before the First World War. But today, problems still arise, even on the best-run hole. This crew, like all crews working for BP, have every mechanical and electronic device available to help them optimize drilling performance. However, they are drilling in the dark, and the unexpected can happen.
Call the company man. I think we've backed off.
The men who worked the earliest fields held a key advantage over modern crews. They literally dug the wells so they could monitor the condition of the subsurface minute by minute and take appropriate actions. The key to success then and now is knowing how the rocks react to drilling and what can be done to control them. It's just understanding what is beneath your feet. Drilling, at least on a workshop scale, is straightforward. The right choice of bit, speed and torque for a particular material, plus lubrication, should ensure success. Even if we can't see through what we're drilling, there is every chance that the material is homogeneous. It's the same all the way through, and in nearly all cases the material is stronger than the forces acting around the hole, so there will be no distortion during drilling. There is one other certainty in the workshop. The lubricant is not going to disappear into an unknown fracture. Oil field drilling may certainly be on a larger scale, but the greatest difference is that the material being drilled is out of sight, usually unknown and not consistent. Most importantly, unlike the workshop experience, the hole will not be stable. Just a few meters below surface, if not supported, it'll tend to change shape, leading to tightness or even collapse and hole failure. The reasons are simple to see. In a trench on a typical building site, forces tend to push the walls of the trench inwards. Just the weight of 2 or 3 meters of soil and rock are sufficient to squeeze the trench closed. Forces in the opposite direction have to be applied by these steel supports to keep the working space open. The same happens at depth. This is a roadway in a coal mine a few hundred meters below surface. It was cut into shales, and when new, a few weeks before this picture, had a perfect shape. The weight of the rock above the roadway has given rise to forces which have pushed the soft rock into the void created by the miners. If the force had acted just vertically downwards, the roof supports would have been pushed through the floor. The distortion of the sides of the roadway and the floor shows that forces are working in all directions. Just to see how easily some rocks move, we put a core sample under a large force in a workshop press. The vertical force moves the rock sideways. In the well bore, the rock immediately around the hole is constrained by all the rock around it. This laboratory rig does just that. It constrains a sample with a hole through it and then applies pressure. The result, a very tight hole. In the trench, the mine roadway and the rock sample, nothing really happened until there was a hole, a space into which the surrounding forces can squeeze rock unopposed. If a well creates a space, what can we do to counteract the forces acting there? Use mud, the right mud. There's no need to remind you that mud in even small quantities can be heavy. The weight of mud in the tube is forcing some out of the holes. In the well, the forces due to the weight of mud act in all directions and support the well sides. Why is the weight of mud so vital? In this simple demonstration, the weight of fluid in the tube pushes the skin of the balloon outwards in all directions, forcing back the walls of the model. If the low-density alcohol is replaced with a higher-density fluid, drilling mud, and the tube filled to the same height, the forces on the balloon are increased and the walls are pushed harder. The same happens in a well. The greater the weight of mud pushing on the walls, the greater the force on the walls. We control the weight of the mud by adding a dense powder, the mineral barite. The more barite we have in the mud, the heavier it becomes. We know that if the mud weight is too low, the hole will collapse. What happens if the mud weight is too high? In the hole in the center of this perspex block, forces are directed at the walls by hydraulic pressure. If the pressure exceeds the strength of the block, it fractures. This sandstone in a major aquifer was fractured long before the drill string punctured it. Water is flowing in large quantities through the fractures. If, during the drilling of sandstone, fractures are formed, the drilling fluid could disappear through the fractures with serious consequences. So, mud weight and the resulting pressure on the well bore are vital. Too low and the well can collapse. Too high and the rock can fracture. The difference between these two levels is the mud weight window. That sounds simple enough. Now for a small complication. Real rocks vary dramatically. During the course of a well, the rock type can change literally hundreds of times. Each change will bring different drilling conditions, which in theory should lead to a change in mud weight. Rapid changes in the mud weight, however, are just not practical. The general practice is to increase mud weights in shales to avoid collapse. However, when a sandstone is encountered, that high weight may lead to fracturing. Lowering the weight at this point will cause the shale to collapse. The mud weight required to support the shale may be higher than the mud weight at which the sands fracture. If there's any suggestion of a shale sequence being followed by a sandstone, it may be wise, if possible, to case off the shale. In summary, weak to intermediate strength rocks with very low permeabilities, such as shales, need higher mud weights than strong rocks or rocks with good matrix permeability, like sands. Too low a weight leads to collapse. Too high, and some rocks fracture. The range of weights which allows support for both and at the same time keep the mud in the well bore is called the mud weight window. Now, a closer look at the rocks to see in detail how mud supports the well bore. In sandstones and other reasonably permeable rocks, most fluids will penetrate relatively easily. When drilling mud is used, the solids in the mud rapidly build up to form a filter cake, which blocks the pores, lowers permeability, and reduces fluid loss into the formation. The filter cake provides a number of benefits, the main one being to allow the mud in the well bore to support the formation. The support comes from the difference in pressure between the mud in the well bore and the pressure in the pore spaces between the grains of sand. As long as the well bore is at a higher pressure and the mud cake effective, this overbalance will ensure support in even very weak, poorly cemented sandstones. This simple model shows the role of a good filter cake in a completely uncemented rock. The box is full of loose sand, and the void of the well bore is sustained only because of the support given to the sand by the fluid in the well bore pushing against the filter cake, the overbalance. If the cake is too permeable and does not effectively seal the rock, the mud penetrates into the pore spaces, pressures equalize, the overbalance is lost, and the well bore collapses. The effectiveness of the filter cake is regularly checked at the rig side using an appropriate fluid loss test. The lower the filtrate loss during the test, the better the filter cake building qualities of the mud. Different tests are used depending on mud and formation types. In shales, capillary effects can be more important than mud cake support. This is a shale seen under a hugely powerful microscope. The platy objects are the clay minerals which form the rock, and it's obvious there are spaces between them, porosity. But the pores are thousands of times smaller than in sandstones. Capillary effects in such small pores stop oil-based muds from penetrating them. The oily mud is unable to displace watery pore fluids which exist naturally in the rock, so the mud gives full support to the well-bore wall. Water-based muds, however, will slowly penetrate shales, leading to a pressure increase in the pores and subsequently causing the shale to become unstable. The shale can expand back into the hole, causing tight hole or hole collapse. In addition to the penetration effects, direct chemical reaction between water and shales can also cause problems. Swelling, softening, and dispersion can occur. This simple rolling test shows how shale disperses readily in water but remains intact in oil. Despite the drawback with water-based muds, they are being increasingly used. New chemical additives are being found which can better inhibit the reactions between water and shale. Oil-based muds are generally more effective, but they do suffer from environmental restrictions and high costs. We have seen that well-bore stability depends on understanding the ways in which mud can support rocks and how rocks react to the mud. But it also depends on understanding the variety of forces acting on rocks beneath your feet. In a vertical well, the vertical force is usually greater than the horizontal forces. As the angle of inclination increases, that vertical force effectively pushes not down the hole, but on the wall of the hole, leading to unequal forces and partial collapse. So increased mud weight must be applied to counter it. That, of course, may lead to a risk of fracturing in other sections of the hole, for example, in sand intervals. Up until now, we have worked with the idea that the forces in the rocks we're drilling through are due to the weight of overburden, and that the horizontal forces are equal in all directions. So as the pressure exerted by mud acts equally in all directions, everything should be all right. But in many situations, the horizontal forces are not equal. In many parts of the world, rocks have been pushed, squeezed and folded, just like this block of foam. The forces which cause this distortion do not just disappear. In effect, they can be stored. This means that when a well is drilled, the forces acting on the void won't be equal, and the well can be squeezed more from one direction than others. The only way of accurately assessing if this is happening is by the use of caliper logs. This log, showing borehole geometry, is from a vertical well in the Cusiana field in Colombia. One of the calipers is nominally the same diameter as the bit size used, and the other caliper is overgauge. Over some sections, the overgauge is considerable. Why is the borehole spalling in one direction and not the other? The reason has to do with the Earth's stresses being unequal. BP operate other fields in less obvious stress regimes, which also suffer interesting problems. This is the Ula field in the Norwegian sector of the North Sea. The vertical exploration and appraisal wells and the first few inclined development wells were drilled relatively problem-free. However, as development progressed, certain inclined wells were found to be significantly unstable in the shale sections. Two particularly difficult wells were A07 and A17, both requiring 3 sidetracks to reach the well target. Initially, the hole instability problems were thought to be related to chemical interaction between the mud and the shales. A number of attempts were made to find the right mud chemistry, all to no avail. Work was carried out to study the stress state in the overburdened shales. This showed that the horizontal stresses were unequal with the larger horizontal stress directed approximately northwest-southeast, which is parallel to the axis of the problem wells. Further analysis showed that inclined wells with azimuths close to the larger horizontal stress direction are the most at risk to hole instability. This explained the reasons why problems were seen in these wells. The solution to counteract the adverse stress state around wells with these azimuths is to increase the mud weight. In well A07, for example, initial unsuccessful attempts to drill the 12¼ inch hole were made with the same mud weight as used on the first development wells. Finally, the whole section was drilled successfully only after a significant increase in mud weight. In exploration and production anywhere in the world, careful examination of stress fields derived from caliper and dip meter logs allow further wells in the same area to be planned. Planning can also help to optimize a mud system for the entire hole.
But of course, it's a pretty good gauge, isn't it?
Yeah.
Productivity and safety depend on a stable well bore, and that will follow if all involved in drilling understand what's beneath their feet and what they can control in the drilling process. Mud supports the well bore. Too light, and there's not enough support. Too heavy, and fracturing can occur. Oil-based muds do not penetrate shales or react strongly with them, but can cause environmental problems and are costly. Water-based muds are cheap and environmentally friendly, but tend to penetrate and chemically react with shales, leading to instability. Improvements continue to be made, bringing them closer to oil mud performance. The right mud will build a filter cake in permeable formations, which allows the mud to support the wall. The inclination of the well affects the weight of mud required. Stress inherent in the rocks can affect stability. Understanding the stress field and choosing the right direction or azimuth to drill can minimize the effects.